Today's presentation in the Geotechnical Engineering RSR as part of our NHERI uh, Graduate Student Council. We are pleased to invite Dr. Jasmine Bekkaye, and she will present about uh, her work from research to industry entitled From Disaster Debris to Geotechnical Advancement and Interdisciplinary Perspective on Infrastructure Resilience. And Dr. Jasmine Bekkaye is a geotechnical engineer with a PhD in civil and environmental engineering and a bachelor's in environmental engineering from Louisiana State University, LSU. She is experienced in geotechnical subsurface investigation, soil characterization, engineering analysis, UAVs, and photogrammetry. Uh, she is also experienced in GIS and remote sensing, machine learning, data science, and data visualization. So that's a lot. It's that's a lot to cover. And I hope that Jasmine will cover this part today, how she's correlating what she has learned in grad school and her PhD research into her current job at Crawford and Associates. Thanks, and Jasmine, you have the role.
All right, let me share my screen. I'm going to do one thing first. Okay, so everyone can see my slides and all that?
Yes.
Awesome. Thanks. Well, yeah, hi again, everybody. Thank you for giving me this opportunity to come speak to you guys at the Geotechnical Research Subcommittee meeting here. I'm a proud alumni of the NHERI GSC, so I love to see the events and the presentations that the group puts on and organizes. So it also makes me really happy to be here now presenting to you all. So today I'll be giving a talk titled From Disaster Debris to Geotechnical Advancement, an Interdisciplinary Perspective on Infrastructure Resilience. So just to kind of go, did it change slides?
It did not.
It's kind of, okay. There, okay.
Yeah.
Oh, there's just like a little lag. Okay, I think we'll figure this out. There we go. So to kind of just give a little more into my background, I've done really a wide variety of work within the civil engineering field, both in research and practice now. I got my bachelor's in environmental engineering from LSU. And during that time, during my undergrad, I got really interested in geotechnical engineering after taking the intro class there. So I started an internship, a geotechnical engineering internship during that time with geoengineers. And upon graduation with my bachelor's, I started working full-time as a geotechnical engineer with them. And then I continued to like it so much that I wanted to go back to school for it and just kind of learn even more about it. So I went back to school at LSU and I started my PhD in civil engineering with a concentration in geotechnical engineering. I graduated in the fall of 2024, and my coursework was concentrated on geotechnical engineering, but my research was kind of a mixed bag of a lot of those things with a big focus on natural hazards. So I did a lot of research on different remote sensing techniques for assessing the impacts of natural hazards on natural and built environments. I also worked on developing reconnaissance methods for post-disaster data collection, and that culminated in my dissertation, which is titled Advancing Data-Driven Disaster Debris Characterization and Quantification. So then, kind of upon my graduation with my PhD and right before, I was kind of bouncing between the idea of academia and industry. I kind of ended up just deciding and ending up in industry. And I now work at Crawford Associates. We're a small geotechnical engineering firm that's rapidly growing to a mid-sized firm. And we serve Northern California and beyond. And I mainly work on public works projects. So we do a lot of work with cities and counties on any kind of public works infrastructure. So bridges, levee design, highways, things like that. And so, as you can kind of tell, my research area and my current field aren't super directly related, but I'm going to go into today about how I've just really integrated aspects of my research into my practice now. And I'll try to accommodate this lag thing, I guess. There we go. Okay. So, the overarching theme of this presentation is how my doctoral research has influenced and been integrated into my field of practice now. So I'm first going to focus on two chapters of my dissertation. The first focusing on emerging technologies for disaster debris quantification, and the second is on machine learning-driven geospatial analytics for disaster debris management. Then I'm going to move into how I'm integrating the tools and the skills that I used and developed during my research career into my geotechnical engineering practice now. So I'll show some applications in spatial modeling and geotechnical engineering, subsurface exploration planning with UAVs, hazard assessment and data recon, and then looking ahead. So just kind of briefly talking about some future ideas on how I plan to continue converging research into my practice. So with that, I'm going to move into the chapter on emerging technologies for disaster debris quantification. So very brief background on disaster debris. One of the consequences of extreme events is the generation of these immense amounts of disaster debris. And that creates these cascading economic, social, and environmental impacts to communities. So at the time of my research, the application of some emerging technologies, including UAVs, drones, and LiDAR for quantifying disaster debris really hadn't been looked into yet. So what I wanted to do with this study was demonstrate multiple remote sensing tools available for quantifying disaster debris, compare the performance of each tool, and provide recommendations for selecting a tool based on desired application and available resources. So to do this, I use Southeast Louisiana, where I'm kind of originally from, and Hurricane Ida in 2021 as a case study. And for this presentation, I'm only going to highlight kind of this first objective here, and in particular using UAVs and terrestrial laser scanning to quantify disaster debris at a staging site in Grand Isle, Louisiana. So to quantify debris using UAVs or unmanned aerial vehicles, I conducted a UAV survey over this debris staging site in Grand Isle after Ida. And so the goal was to collect aerial imagery to be processed into a point cloud using structure from motion photogrammetry techniques. And so that process is shown in the workflow here. This involved placing and surveying ground control points to get accurate geolocation and elevation, and then planning and conducting the flight, and then processing that data into a point cloud. So then the point cloud generated from the imagery was used to quantify debris volumes. So to quantify debris using terrestrial laser scanning, or TLS, I conducted a TLS survey at the debris staging site directly following the UAV survey. So this involved placing the scanner around all of these debris piles here that you can see. And so when the scanner is in each position, it takes one scan. So then following the survey, all of the scans are compiled into one large composite scan of the entire area. So then that composite point cloud from all of the scans is used to quantify debris volumes. So what I found from the UAV and the TLS surveys is that both methods are highly effective for quantifying debris, and they can provide precise volumes. So this figure on the top is showing the UAV imagery on the left, segmented debris piles from that point cloud in the middle, also with the 3D meshes that were kind of created to show relative heights of the piles. And on the bottom, it's showing the same thing, but using the terrestrial laser scanning data. So looking at these two data sets and comparing them, you can see there's these gaps with missing data in the TLS point cloud. And so these gaps are in parts of the pile where the exterior of the pile is taller than the interior, or there were obstructions. And so one of the consequences of a TLS survey being conducted on the ground is that it's unable to scan through obstructions or things that are in front of it as it's trying to scan the area. So to kind of look into this a little further, I created these subsections that are within the white polygons that you can see within these piles. And so I wanted to make these subsections in areas where there aren't data gaps in order to compare the volumes in those areas that aren't missing any data. So now comparing those volumes, this figure here illustrates the debris volumes from both methods. The graph on the right is showing the volumes, or sorry, let me start with the left. The graph on the left is showing the volumes of all of the debris piles across the entire area. It's including those missing data areas as well. And then the graph on the right is showing the volumes of the subsections that are within those white polygons of each debris pile. So as you can see the graph on the left, the methods calculated volumes within 8% of each other, but you can see the TLS volumes, which is the orange in this graph, the UAV volumes are blue. The TLS method estimated higher volumes in debris piles 1 and 2. Now, when we look at the graph on the right, you can see the volumes are much closer in those areas without the missing data. Excuse me. And so the discrepancies in these volumes between the methods is likely due to how Cloud Compare, which is the software I use to calculate the volumes from the point clouds, how it interpolates across the missing data areas. So it's likely that it just assumed this larger value based on the data around it, and that's why the volumes might be larger from that method. So that kind of concludes the emerging technologies chapter. Now I want to move into machine learning-driven geospatial analytics for disaster debris management. So the motivation behind this study is really that current disaster prediction models are pretty inadequate, and unsupervised algorithms really have yet to be utilized, at least at the time that I did this study, and that could help guide flood debris models. So what I wanted to do with this study was demonstrate a hybrid unsupervised and supervised machine learning approach for understanding the relationships and drivers influencing flood debris quantities across a region. And so this hybrid approach was selected because initially just looking into supervised regression models alone still resulted in pretty unsatisfactory performance. So the machine learning approach proposed in this study is kind of shown in this framework here. It first involved, oh no, all right, almost. There we go. Okay. So first, it involved acquiring and aggregating the post-disaster waste data. So that is, you can kind of see it shown on the figure on the left there. That's showing debris removal data from Beaumont, Texas after Hurricane Harvey. And each of those red dots is a coordinate location of the debris removal that also had a tonnage and a volume associated with it. So by the time Hurricane Harvey reached Beaumont, it was downgraded to a tropical storm. So the main hazard experienced in this area that developed all the waste was really just flooding with very little to no wind impact. And so for this study, I also, to kind of make it a little easier on the unsupervised algorithm, I clustered the data to the census block level. So those are the white polygons that you can see in that figure as well. So then now with that aggregated data set, I wanted to identify and characterize the drivers of flood debris. So I selected 19 explanatory variables there. It included things like flood depth, elevation, square footage of the residences around. I also conducted statistical testing on the clusters to try and evaluate patterns between the flood waste and the drivers. Then I built a random forest model, a random forest classification model using the cluster data. And then once we have that model, I evaluated the performance of the model for debris prediction. And I also wanted to look at the relative of importance of each variable in model construction. So for this presentation, I'm just going to focus on how the random forest classification model performed, and then how the actual data clusters from the study that we got the data from compared to current debris prediction models used in practice. So this is showing the confusion matrix that was generated from the model for the validation data and the blind test data that I used to test how the model was performing. It shows the percentage of correct and incorrect predictions for each cluster. So the correct predictions are in the diagonal boxes here, and all other boxes show the incorrect predictions classified by the cluster. So here, cluster 1 is high debris amounts, cluster 2 is medium debris, and cluster 3 is low debris in terms of tonnage of debris waste. And so with these accuracies, you can see they should be a little relatively closer in value. And so some of those discrepancies can be attributed to data splitting. So the blind test data likely had more samples that were easier for the model to predict. However, I did try to address this to the best of my ability in the model's construction. It's just kind of hard sometimes, so that's how it goes. As you can see, the model most accurately predicted cluster 2, which is the medium debris class. It had a success rate between 69% to 75%, and it performed worse for clusters 1 and 3. And those are the high and low debris classes. And so that had a success rate of 54%, and then 61% for the high debris class, and then 52% to 57% for the low debris class. So the last thing I really just wanted to demonstrate here was why this study matters. So I wanted to compare actual data that we got from the debris removal operation to estimates generated by the HAZUS flood model, which was the current state of practice for flood debris waste estimation. So to do that, I input the same flood depth grid into the HAZUS program and generated those estimates from HAZUS. And then I categorized the estimates into their respective cluster, if it was a low, medium, or high debris cluster. So the biggest takeaway here, which the left is the map showing the debris tonnage clusters, the actual data, the right is the HAZUS flood model estimates. You can see how HAZUS significantly overpredicts debris. And so over predictions of debris can place these heavy burdens on emergency management officials. And so these maps of the clustered flood debris predictions can aid disaster debris removal and management operations. So for example, in the map, you can see areas where there might be high debris tonnage forecasted versus areas with low debris tonnage forecasted. And so that can help governments and counties and people working on the removal operation allocate more resources to census blocks with higher debris amounts compared to lower debris census blocks. So just kind of helping create a more efficient debris removal operation. So with that kind of background on what I focused on my research and dissertation, I kind of want to move into some of the applications I've worked on at my job now on how I've been able to use a lot of the things that the tools and methods I used and how I can apply them to my geotechnical engineering practice. So first I want to talk about some things I've done with spatial modeling in geotechnical engineering. So this project we actually just submitted the 30% design report for it. It's a really big project. It's a large-scale effort and levee design project in Reno, Nevada, with the goal of providing flood protection to the Reno and Sparks area. And so this is an area with currently poor to no flood protection infrastructure, and they have a history of repeat and worsening flooding over time. And so between these maps too, you can see the large number of borings and test pits that we did as part of this project. I did at least half of them. It's a pretty fun site, actually. And so the top left map is showing the current elevation of the area. The bottom left is showing a model of the proposed elevation after the construction of the levee, river terracing that they're proposing, and realignment of the Truckee River here. So to build a levee, you need a lot of soil. And so part of a levee design project is identifying suitable borrow areas to derive your levee fill material from. In this case, that borrow area is within the river terracing that they're going to do because they're doing a lot of large excavations there. So what I wanted to do was, since I have these kind of GIS and remote sensing skills of using these data sets, they haven't really used this approach at my current company before, But since I already know how to do this, I kind of had the idea of taking these data sets, subtracting out and doing some calculations within QGIS and creating a map of proposed excavation depths to tell them how much of each area they would have good levee material to the proposed excavation depth. So all of these kind of pink dots in the middle are test pits that we did. And as part of the subsurface program, we were able to characterize how much is good clay material and then when it turns into gravels and cobbles. So with this map, we can look at, okay, here they're proposing to excavate 8 feet of soil, but we only have 4 feet of good levee material. So that kind of helps create a better estimate of what we call a waste estimation factor or a waste factor. And that's for cost estimating. So they have to be able to estimate how much soil they're going to import for the levee versus how much they'll actually be able to use at the site. Now I want to talk about using UAVs for subsurface exploration planning. So drones and UAVs are still not standard practice in geotechnical engineering. A lot of companies are beginning to use them or have already been using them, but a lot have kind of just started. And my company is one of those examples. So luckily with my drone background, my company was pretty eager to purchase a drone. And they also see the benefit of how this tool can advance our practice, in particular with storm damage sites. So Northern California is prone to landslides and road washouts due to atmospheric rivers and winter storm events. And that can create these areas you can't access on foot, but you still need to perform geotechnical testing in the area to be able to determine the depth of the failure. So this project that I'm going to show you some drone video for, it'll probably be a little laggy, but we'll see what we can do. It's a levee erosion repair project in Bear Creek, which is in Merced, California in the Central Valley, where in January I brought the drone out with me to the initial site visit to collect imagery and videos documenting the damage. And that will also help me determine access concerns and restraints when I'm planning my own subsurface exploration this summer. And that's going to involve performing dynamic cone penetrometer tests on the waterside toe of this embankment. And also we're doing borings on the crest of the levee. So I'm going to see if this will play. It'll probably play in a little spurts, but you kind of get the idea. So for documenting the damage, you can see how the drone video here is able to show areas at the site that are hard to see and document on foot because we had to walk around this crest, and you can kind of see there's a lot of vegetation on the creek banks, which is really hard to see through if you're only on one side of it. And for subsurface exploration planning, for me to be able to get to the waterside toe, as you can see, is kind of a predicament here. So I don't want to slide down the slope on the unstable section because I have to do testing here in order to see how deep that failure is. So having this video that I can review as I'm planning my fieldwork can kind of allow me to be better informed about where my access points are and where they aren't in order for me to conduct fieldwork, which is substantially better than what we have been able to do with this so far. And the last application I want to talk about is hazard assessment and data recon. This is some fieldwork I actually just completed a week or two ago, which is for a project where we conduct annual bridge monitoring at the Cochrane Bridge, which is south of San Francisco and San Jose here. And so this bridge was designed and constructed to withstand a certain amount of displacement on either end because it is located over the Calaveras Fault, which I think it's this picture on the right here. You can kind of see it's a faint orange line that goes through either side. And so that fault is a major branch of the San Andreas fault system. It's a right lateral strike slip fault. And so that means the west side of the fault moves northward relative to the east side. So in this picture, the base of these yellow arrows here is kind of showing what we imagine that relative movement happening by the bridge to be. So at this site, there are inclinometers, extensometers, and tilt meters installed to measure displacements so that we can gauge how quickly it is moving each year. So with us just having this new drone we got, this was the first visit where we could bring it out and actually get aerial imagery of the site and be able to look at the site on a much larger scale. So as you can see, we can not only differentiate the plane on which the land is moving, which might be a little hard to tell, but it's kind of where we imagine the faint line between those arrows where it's a little more vegetated. That part of the mountain ridge, I guess, right there is moving a little that way. And then the part where the bridge is kind of coming towards you where you're looking at the picture. So we can kind of see that a little better, but we can also take a look at even more slides that are occurring in these damage areas that are under the bridge that we weren't able to see on foot because it's really dangerous and difficult to get down there. So you can actually see there's some damage on the concrete apron on that left bridge abutment. And with this image too, we can compare to previous years where we saw it has been there. So it's been there for years, but I didn't know that. So when I took the image, I was like, oh man, that does not look good. But that's why we have repeat images. So those are kind of some things I've already done. I also kind of want to talk about some ideas I've had for how I can kind of continue integrating all these things moving ahead. So really the problems we face in geotechnical engineering as a result of hazards such as landslides, settlement, and seismic failure, they don't really respect disciplinary boundaries, so our solutions to them really shouldn't either. So some ideas I have on how the emerging technologies and AI and machine learning tools that I use in my research can continue to be integrated into my practice include things like automatic change detection. So we can conduct repeat UAV surveys, for example, at the Cochran Bridge site, and then pair that with AI anomaly flagging to detect any really substantial movement that has occurred over time. And that would require a lot of training and high resolution imagery, but it would still be a really cool project for me to work on. I also want to kind of start integrating machine learning for vulnerability prediction. So the real power here would come from feeding multidisciplinary data, not just geotechnical subsurface data, but hydrology, land use, seismic history, and put that into models so that we can learn what conditions precede actual failure. And so that's really just a fundamentally different risk framework than factor of safety alone, which is where us geotechnical engineers often live for most of our projects. And then with UAVs and subsurface investigation, we can develop high-resolution surface models from UAVs, but they're really only part of the picture. So if we can fuse this with boring logs, CPTs, and instrumentation data, we can kind of start building these true 3D site characterizations rather than inferring from limited points and just have a better picture of the site overall. And then with instrumentation interpretation, we can use, with our inclinometers, extensometers, and tilt meters, these already generate this continuous data that can sometimes be difficult to process and interpret, which is kind of what I'm going through now. But with AI-assisted threshold flagging, we can kind of create a model that's set up with these different thresholds across all of the combined instrumentation that can alert us before movement becomes failure. So instead of just monitoring and interpreting, we can easily evaluate early warning using all of the combined data. So with that, I wanted to thank you all so much for listening to me talk and enjoy my various background of experience and how, all of the stuff I get to do in grad school, I still get to kind of apply in what I'm doing now, even though it's a little different. And if you have any questions, yeah, definitely let me know. This is also my email here if you just want to reach out or have any questions down the line. And thank you again.
Thank you so much. Thank you, Jasmine. That was great. That was very, very, very informative and very, very, very comprehensive to me. I would like to open the room for any questions from the audience. Any question to Jasmine?
I don't have a question,
Yeah, go ahead.
but I really appreciate, Jasmine, how you showed what you did in your dissertation, the skills that you learned, um, the instrumentation that you used, and how you're applying what you did. Even though it is different, you're adapting these on the fly to improve mitigation and warnings that can help um, the clients that you're working with now. I think that's very interesting.
Yeah,
Yeah,
it's
thank you.
it's really great.
I definitely
So
enjoy it, and it's nice to not have to sacrifice a lot of the things I enjoyed and skills I enjoyed in school, and how we can actually continue to do things with them for other applications where they're very useful.
yeah, sure. So Jasmine, I want to go back to the Levy project.
Yeah.
I just have some question. So so here was yeah,
Oh, this one or the other one?
uh, this one.
Okay, let me come on now. There we go.
Yes. So here for the, I think you mentioned the subsurface investigation, right?
Yes.
So you are planning to do DCBT or Banda on one side, and then you are gonna do like boring on the other side, right?
Yeah, we're gonna do borings on the top of the embankment. And
Yes,
then I wish it was the Panda DCP, but it's a little worse. It's like this huge metal, I guess what the traditional one is, where you lift it
yeah,
up and drop it.
understood. Yeah, you just left with a number of drops.
hmm
There's no QD or like any resistance. So uh, I mean, why? So I have two questions. Why not DCBT on both sides? And then what is the objective? Like, are you gonna do like slope stability remediation? You're gonna enhance the slope.
Yeah, this project's kind of interesting because we're not doing slope stability analyses, and we kind of do that for a lot of projects. I guess one of the big overarching answers for especially investigation and stuff is budget and money, which is something I'm learning in the
Understood.
consulting world.
Understood.
So that's most likely why we're not doing DCPs on the other side of the embankment, but the other side of the embankment also doesn't have any failures that we noticed. So I think one thing is we probably would have wanted to add some if we did notice any failures on the other side.
Understood.
But most of the failures we noticed is because when they have these really heavy rainstorms, it just runs right through this creek here and erodes part of it. So it's a combination of we didn't see failures on the landslide, and we probably don't have enough budget to do all of it.
Yeah, sure. Okay. Uh, uh, One more question about the bridge. So, do you think uh, I don't know who owns this bridge or like who operates it, but don't you think that's a very obvious digital twin question, right? If we like just imagine if we have it with all of these data, the land movements in kilometer, all of the equipment that you mentioned and the data that you have, that's like guys, that's a digital twin.
I completely agree. I think that would be awesome to have here. I think it's another one of those things where I'm noticing how much budget really influences a lot of things. I don't know if it's owned by the city. I think it might be owned by the county. And one thing that's kind of nice is counties in California have a lot more budget for projects than what I'm used to in Louisiana. So it's still like a lot more open than what I'm used to, but I think that would be a great idea. And I think part of it too is they just don't know about those things. Like they don't know about the option of being able to create a digital twin at something like
Yeah,
this site where there's so much movement and catastrophic things that can happen if, something were to happen. So I think too, it could be just a lot of kind of educating to show what kind of technology people can be using for these things. Because I don't know, you get so used to, I think we put these, well, not we, but the company that my current company bought out a different company in 2012, I think, and they put these inclinometers here in the 80s. So I think,
oh,
they started it then. They said this is the way, these are our workflows, we're going to do that, and they kind of just stuck to it. But I think even just like more people being aware of that being an option would kind of help something like that.
that's cool. That's cool. Okay. Thank you so much. Thank you, Jasmine. I appreciate it.
Yeah, thank
Eh,
you again.
Yeah, sure. Any other questions? Okay. I think uh yeah. So thank you, Jasmine. It was a pleasure to have you presenting to us today. Very, very interesting work, and I really, really enjoyed how you were able to combine your research experience with the current project that you are working on. And best of luck in your future endeavors. Thank you.
Thanks, Mohammed. Thanks
Thank
again
you.
for giving
Sure.
me an invitation to talk.
Sure.